In this video, we're going to do example 2.4.2, which is going to be about finding the shortest distance between lines L1 and L2. Now, we have to remember from a previous video that there are different formulas and different situations which might occur here. If our lines are intersecting or coincident, then the distance between them is 0. If the lines are parallel, then we're going to use a point to line formula. And if the lines are skew, well, then we'll use the formula that we derived in our previous video. So the first thing that we have to do is decide what the relative position is of our lines, and then we can apply the appropriate formula. So let's go back to the problem and determine the relative position of these lines. So the first thing we can see on line 1 is we can see the point that is given by the constants. So our point P1 is the point 4, minus 1, 3. We can also see the direction vector that was used to define L1. That's the coefficients of t, so 0, 1, minus 2. L2 is in symmetric form, so we have to remember that this is all equal to t. And if we put it into parametric form to make it a little bit more readable, we will get x is 5 minus 3t, y is 8 minus t, and z is 17 plus 4t. And so we can see a point on L2, a point 5, 8, 17, and we can see direction vector for L2, minus 3, minus 1, 4. And so obviously the direction vectors are not parallel. I say obviously because they are not multiples by inspection. There is nothing that I can multiply the first component of d1 by to give me, right, minus 3. Nothing times 0 can ever give me minus 3, so I know that those are not multiples, and therefore they are not parallel, which tells me that the lines are either intersecting or skew. So to go further, we need to decide whether they are intersecting or skew, which means that if we remember from our relative positions toolbox, we are going to, not example, we are going to examine the triple scalar product. P1, P2 dotted with D1 cross D2. So P1, P2 we can calculate by subtracting the coordinates of P2 minus the coordinates of P1, and so I'm going to get 5 minus 4 is 1, 8 minus minus, so 8 plus 1 is 9, 17 minus 3 is 14. Now D1 cross D2, let's evaluate that. So D1 cross D2, D1 is the vector 0, 1, minus 2, D2 is the vector minus 3, minus 1, 4. So a little bit of recopying here. Minus 3, minus 1, 4. And what do we get? We get 4 minus 2. So that is 2. And then 6 minus 0. And then 0 minus minus, so 0 plus 3. So we want P1, P2 dotted with D1 crossed with D2. So we will dot the entries of P1, P2 with the entries of the cross product. And we are going to get 1 times 2 is 2. 9 times 6 is 54, plus 3 times 14, 42. So 96, 98. And in particular, that is not 0. So the lines are non-coplanar, and therefore they must be skew. And if the lines are skew, well, we know which formula to use. Then the distance between skew lines is the absolute value of the triple scalar product. Well, that's kind of handy. We've already calculated it. D1 cross D2 divided by the magnitude of the cross product. So that means it's the absolute value of 98 divided by the square root of, and so I can take the components here, 2 squared plus 6 squared plus 3 squared. So absolute value of 98 is 98. 40, 49, root of 49 is 7. 98 divided by 7 is 14. The lines are skew, and the minimum distance is 14 units between them.